Okay, so we start our video lecture 10. Now we address the problem. I asked you to do a system with MN, MG, etc. and there were some questions about rhodonite, etc., etc. So I would like to clarify a few points here. Before that, from the last lecture, we understand that even when you have a mineral where it is a solid solution between the different phase components, like last time, CSiO3, MgSiO3, FeSiO3, they have different crystal structures, largely dictated by their ionic size and also charge, which I have not touched upon here, but it's true for plagioclase, which you know. So what happens, every mineral that you see, every phase component that you choose, these phase components are not identical. They have major to small differences between these ionic, they have differences in crystal structure. So since they have differences in crystal structure or the microscopic or the micro level or angstrom level properties, their macroscopic thermodynamic properties are also different. So essentially every phase component has a different equation of state in chemical thermodynamics. They all have. We will talk about those later, but at the moment this would suffice to make a beginning to that question. Let's say when we are talking of a pyroxene, say MnMgFe, SiO3, we know that the ionic radius of manganese 0.8, magnesium 0.66, Fe 0.74. Mn and Fe, they are very close in size, separated by 0.06 micron. And Mg and Fe, Mg is 0.74, Fe is 0.66, so 0.08 angstrom is the difference. So what we can see, that the structures are not widely different, but there are subtle differences. And therefore each of these components, what are they? MgSiO3, FeSiO3 and MnSiO3, they are distinctive phase components. And what is the phase? Mn, Mg, Fe, SiO3. This is the phase. There is not two phases. There is one phase, which is a solid solution of MnSiO3, FeSiO3 and MgSiO3. Three phase components. And we know that the structures of all the three are going to be different. So they will have different thermodynamic properties. Right? Now, some of you said that it should be a separate rhodonite phase. No. For example, let me say my pyroxene, the phase, if I have analyzed it and found out that this is the composition. Say for example, okay, so I take a triangle, this is a composition space. This is a composition space where you have MnSiO3, MgSiO3 and FeSiO3. And my orthopyroxene that I am talking about, say has this point. So the orthopyroxene phase has a composition that plots at this point in this triangular composition space. So how do I find out what is the proportion? Here MnSiO3 is 100%, Here FeSiO3 is 100% and here MgSiO3 is 100%. So this is 50, this is 50, this is 50, this is 25, this is 75. So it goes. Right? Now, if this is the composition, then this can be resolved into the 3 end member components. Right? MnSiO3 is 100% here, but at the baseline, MnSiO3 is 0%. At the baseline, there is no MnSiO3. So the MnSiO3 component increases to 100% here. Similarly, the MgSi if my phase was on this line, then it is on the binary MnSiO3, FeSiO3. So there is no MgSiO3. So from here to here, MgSiO3 increases from 0% to 100%. Have you understood? And here FeSiO3 is 0% along this binary and increases in the internal space, and at this point, vertex FeSiO3 is 100%. So if I have a point here, then what I do is, I draw a line parallel to this binary. So I draw a line parallel to this boundary. Have you understood? If I do that, then you can see this is 0% MgSiO3, this is 100% MgSiO3. So how much Mg is there? You can see it. This is 25, this is 50, this is, how much MgSiO3? This is 75, 50, 25. So as I have drawn it, it looks like Mg is 25. It's less than 25. It's, say, around, let's give a value, it doesn't matter. Say, for example, MgSiO3 is 15. MgSiO3. Here it is 0. At this point it's 100. So you can imagine several parallel lines, and here you can say Mg is 15. Now I want to find out what is Fe. So what do I do? FeSiO3, you can see here, this is FeSiO3. So this is the line where FeSiO3 is 0%. So I draw a line parallel to this. So if I do this, then you can see this line, which essentially gives you the amount of FeSiO3. So FeSiO3 is possibly 10. Oh, no, sorry. MgSiO3 is not 15. MgSiO3 is much more, because this is 0% MgSiO3, this is 100% MgSiO3. So Mg is, say, roughly 10. So if Mg is 80, Fe is 10, then Mn should also be 10. Let's say here, this line, this is the amount of Mn in the sample. So now your composition, therefore, is SiO3, or you can write Mg 0.8, Fe 0.1, and Mn 0.1. The total adds up to 1 SiO3. So that is my composition of my pyroxene, in which 80% is enstatite, ferrocylite is 10%, and MnSiO3 rhodonite component is 10%. It is not pure rhodonite. It is the rhodonite component, the rhodonite molecule. Yes, the rhodonite molecule in orthopyroxene will have an equation of state, which is different from MgSiO3 and which is different from FeSiO3. So each of them will have different equations of state, macroscopic thermodynamic properties and equation of state. But I think what you people are mistaking, or some of you, or maybe all of you, I don't know, you are conceptualizing the phase differently. I will tell you, there is something called, and we will come to this, that is why it's better to say it, something called a mechanical mixture. It's called a mechanical mixture. And there is something called a chemical compound. There are two things. This you were taught in school. You have forgotten it. This is chemical compound and mechanical mixture. Mechanical mixture is like, say you add sugar and salt. Sugar and salt. Say you take 10% sugar, 90% salt and mix it. If I ask you, separate it, you will be able to separate it. You can separate it many ways, physical processes, or you can separate it even by picking, because sugar and salt have different crystal structure. So if I give you this mixture, it's a homogeneous mixture. It's a homogeneous mixture, and I give you on a glass plate and ask you to go into a binocular microscope and pick out salt and sugar. And if you know the physical properties, you can separate the salt and the sugar. Have you understood? This is what is a mechanical mixture. In which case, you get pure sugar and you get pure salt. That is mixed mechanically into the salt plus sugar mechanical mixture. But in a chemical compound, if you have MgSiO, sugar and salt as a chemical compound, then you cannot distinguish, or you cannot physically separate the two components. You cannot. That's the difference between a compound and a mechanical mixture. What I think what you're looking at as a phase, as a mechanical mixture of three molecules. That is why you're talking of rhodonite should be a phase, because in your mind you still think it's a mechanical mixture. It is not. It's a chemical compound. This orthopyroxene phase is a chemical compound which we call solid solution phase. It's homogeneous, it is a solid solution phase where all these three components are there in this proportion and they are not separable by physical means. Dry sugar and dry salt can be separated by physical means. Have you understood? We are talking of chemical compounds. I will tell you the thermodynamics of how chemical compounds can become mechanical mixtures. That is a completely different issue. But when I say there is a phase is a chemical compound, it's a solid solution where the three components cannot be physically separated. But the three components have three different equations of state in terms of GHVS. They are different equations of state simply because their structures are not same. But the structure of MnSiO3, where the value is 0.80 angstroms, is similar to FeSiO3, which has an ionic radius of 0.74 angstroms, and MgSiO3, which is 0.66 angstroms. You see, FeSiO3 is quite close to MgSiO3 and it's also close to MnSiO3. But MnSiO3 and MgSiO3, you're separated by 0.14 angstrom. That's a hell of a lot of structures. That is a hell of a lot of difference in structures. So obviously, all the three components have different structures and therefore different microscopic properties. Yet, they form a compound, a chemical compound, which we call solid solutions, because this compound forms in the solid state, unlike sugar solution in a liquid state. So I think I have made my point clear. I will give you another example to clarify the point. I don't know your strength of mineralogy, but there is something called the quadrilateral pyroxenes. This is about pyroxenes in the system CaMgFe whole twice Si2O6. This is a quadrilateral pyroxene. Why? I will tell you. This is CaSiO3. The name for this phase, if it occurs separately, is called wollastonite. This is MgSiO3 and this is enstatite. And you have FeSiO3, which is called ferrocyanide. In this triangular diagram, all pyroxenes form which do not contain sodium, aluminium, ferric iron, titanium, and a host chromium and a host of other elements. These therefore are called non-quadrilateral compounds. Non-quadrilateral compound. If the non-quadrilateral component is more than 10%, then it is no more a quadrilateral compound. And the pyroxene is non-quadrilateral. Why quadrilateral? You say, so where is quadrilateral? It's very simple. Here, for example, at the midpoint of it, you have CaFe Si2O6, right? This is called Heidelbergite. And here at the midpoint, you have CaMgSi2O6, and this is called diopside. You know, I think, this forms the solid solution clinopyroxene, and this binary forms the solid solution orthopyroxene. It is highly simplified. This, what people say, is highly simplified. This is not correct. This is not enough. These two are called clinopyroxene because, once again, calcium has an ionic radius of 0.99 angstroms. Magnesium is 0.66 angstroms and iron is 0.74 angstroms. So you can see here, calcium, although this ionic radius, all of them are divalent, yes? All of them are divalent. Magnesium and iron, they have close ionic radius and they are both divalent. But calcium has a very high, compared to magnesium iron, they have very high ionic radius. And I just showed you in the last lecture, lecture 9, I told you that calcium, these two occur in 6-fold coordination, whereas calcium can occur in 8-fold coordination. So you see, because of size considerations, I did it in the last lecture. So calcium occurs in a different crystal site than magnesium and iron, which occur they occur in the cubic site. This is called the cubic site, and this is called the octahedral site. Octahedral site, which means 6 coordination number. The coordination number here is 6, the coordination number here is 8. So if you take clinopyroxene or monoclinic pyroxene, what is monoclinic? What is orthorhombic? Where you have 3 axes, crystallographic axes, A, B and C. And all 3 crystallographic axes are of unequal lengths, but they are at right angles to each other. But in clinopyroxene, the beta angle. What is the beta angle? The angle between A and C axis. Say normally in a crystal structure, when you hold, your B axis is parallel to you, A axis goes right into your heart, and C axis is vertical. That is the way crystals are held. Now what happens, this is the C axis, but they are of unequal lengths in orthorhombic system, but they are perpendicular, right? But in a monoclinic system, what happens, this vertical axis is no more 90 degree, the A axis changes its slope. This changing of the A axis orientation causes the beta value not to be 90 degree, but something else. It can vary. Why this is done? This is done, this is not a mineralogy class, so I don't draw the whole section and show it to you. This AC meso or non-90 degree, non-orthogonal relationship arises to accommodate the calcium structure, larger calcium in the pyroxene structure. That is why, because clinopyroxene is therefore, you can see, if I take bulastonite, it has a completely different structure than orthopyroxene and ferrocyanide. It has a completely different structure. Because calcium, accommodating calcium, the A and the C axis orientation is off from 90 degrees. So that is why it's called a pyroxenoid. It has a pyroxene-like but not pyroxene structure. Right? So, now say, so I understand you get this point. Now say, orthopyroxenes normally fall in this type of a field. This is the field of orthopyroxene. The width of this field is larger at higher temperature and smaller at lower temperature. We will talk about this in great detail. I'm not getting time because I'm basically, these two lectures was not designed by me. This is forced by you people, your questions. And clinopyroxene has a structure like this. Do you understand? So this is, clinopyroxene occurs in this field. It has a field like this. Again, the clinopyroxene field is, width of the clinopyroxene field is more at high temperatures and less at low temperatures. And lower at low temperature. And there is a small field here. This is called the field for pigeonite. Pigeonite. There is a field for pigeonite. This is called high calcium orthopyroxene. Remember, it is not a clinopyroxene. It's a high calcium orthopyroxene because pigeonite, if it's here, so you see it contains higher amount of bulastonite component in the pyroxene. It contains higher amount of bulastonite in the pyroxene. Have you understood? So we are now going into a more critical question. Now say, I have two phases. Once more I'm repeating. Listen to my words. Don't try to, keep, when you look at when you hear the video lectures, stay within the bounds of the video lectures. You can, at your will, go outside the video lectures, but it becomes more complex. And then understanding requires that you have understood the basics correctly. Otherwise, you will be completely lost and will be writing all nonsense. Right? Let's say I have two pyroxenes. I have two pyroxenes. Meaning, I have a clinopyroxene and a B, an orthopyroxene. These are two phases. One is a clinopyroxene and one is an orthopyroxene. These are two phases. I see in the microscope orthopyroxene and clinopyroxene. I see in the two phases. Orthopyroxene, clinopyroxene. And let's talk about the clinopyroxene and orthopyroxene. Let the clinopyroxene composition be here. And let the orthopyroxene composition be here. This is your A, clinopyroxene, and this is your B, orthopyroxene. Now you see, how do you now find out the composition? What are the phase components? What are the phase components? Very, very critical question, yes? What are the phase components of clinopyroxene? Phase components. Do you see that? That is important. All the three components, CSiO3, MgSiO3 and FeSiO3 are present in both phases. It does not mean that I have a CaSiO3, a MgSiO3. It does not mean that I have a CaSiO3 phase, wollastonite. It does not mean that I have an MgSiO3 phase, enstatite. It does not mean that I have an CSiO3 phase, which is ferrocyanide. No. No way. The two phases are clinopyroxene and orthopyroxene. The plotted compositions are here and here. There are two phases. But the phase components are CaSiO3, MgSiO3, FeSiO3. And CaSiO3, this is in clinopyroxene. This CaSO3 is in orthopyroxene. Similarly, the same three phase components occur in both the phases, but their structures are different. So what is the composition of clinopyroxene in terms of this? Let us see. So, if we want to find out the calcium content of this pyroxene, then you can see, say for example, this is 100% CaSiO3, this is 100% MgSiO3, and this is 100% FeSiO3. Right? So now, what is then Ca content of clinopyroxene? Here you see how much will it be? This is roughly 100. For CaSiO3 0 here. So this will be, say, roughly 48. Ca is 0.48. Right? Then Ca is 0.48. Then what is FeSiO3? You see, if I have to find out FeSiO3, then I draw a line like this. To find out FeSiO3. Here FeSiO3 is 0. Here FeSiO3 is 100. So if I have a point here, you can see Fe will be equal to, say, I don't know, 0.5. Let's say 0.25. And therefore Mg will also be 0.25. Si2O6 or SiO3. This is it. But if you take the orthopyroxene, then you see your CaSiO3 content should be very low. So your Ca may be 5%, which makes it 0.05. And you can draw a line parallel to this here. And this one here, your Mg or FeSiO3 will be around, say, 40%. Fe 0.40, and therefore Mg should be 0.05, 0.45, 0.55 SiO3. The compositions are different. The compositions are completely different. So it is, when I choose the phase component, then I can see that, this point, it does not lie on this line exactly. It lies below it. That means I cannot describe the composition by using the two end members. This one, I can't use it. I could have used it if my component was here. If it was here, right on this binary, I could have done it. But my clinopyroxene point is here, and then therefore I'm off from this binary. So once I'm off from the binary, you have to go into the ternary system. That's what it is all about. So these are two pyroxenes, orthopyroxene and clinopyroxene, and they have these phase components. These phase components are the same as this. These are not different phases. It's not a mechanical mixture. It's a solid solution. It's a chemical compound. And these are the components. And if I plot them on this non-quadrilateral, on this pyroxene quadrilateral, where I ignored all these, then you see this is what is the composition of your orthopyroxene, and this is the composition of your clinopyroxene. If you want to write it on the double formula basis, so you write Ca 0.1, Fe 0.8, Mg 1.1, Si2O6. You're done with? It should add up to 2. 1.1 plus 0.8 plus 0.1 should add up to 8. And if you want to write it the double formula basis, you will write Ca 0.96, Fe 0.5, and Mg 0.50. So this also, no, I think we have made some mistake here. Say 0.27 here, it is better to write. Because it should add up to 1. So this is to 0.96, 0.50, and 0.54. Si2O6. So you see the composition of this solid solution made out of these three phase components is very different from the composition of the coexisting orthopyroxene, which has this composition. I hope I have been able to make myself clear. Phases are not mechanical mixture. Phases are chemical compounds in which each phase component represents a molecule, a chemical molecule, with thermodynamic parameters which are different from another phase component, because there are subtle differences between the two phase components. Am I clear? Right. Thank you. So let's now go over to the third question. I'm really falling back now, because these two lectures that I have been giving are essentially to clarify your doubts, and that is what is cutting into my time. I hope you have understood it. If not, read some books and try to get it. I think I have made myself very clear, and I think you should, for further, I don't want to get into more discussions. It becomes very complex, because all the while, throughout the day, I can't just go on responding to all questions. So that's why I thought it is better that I spend 2 hours and get over it, rather than spending my day trying to answer all questions. Now we come to the last question that we got stuck into in this Google forum, and that is I don't remember who asked the question. It doesn't matter. So we had clinopyroxene, garnet, plagioclase, and quartz. And somebody suggested that I am taking a system NCF mesh. Okay. Let's do it stepwise. Let's say that clinopyroxene is binary between CaMgSi2O6 and CaFeSi2O6. Once again, I draw the formula, draw the pyroxene quadrilateral, CaSiO3, MgSiO3, and FeSiO3, and this is CaFeSi2O6, and this is CaMgSi2O6. So when I say that my pyroxene is a solid solution, I have to make sure that I am anywhere on the boundary. So if that is the case, then clinopyroxene is a phase, and these are the phase components. So we have two phase components. So garnet here will have three phase components, as you know it. So garnet will be Ca3Al2Si3O12, Mg3Al2Si3O12, and Fe3Al2Si3O12. Right? And then you have a plagioclase, and this will lie between CaAl2Si2O8, which is an aurite, and NaAlSi3O8, which is albite. So you have two phase components, and you have three phase components, and quartz is one phase component. Right? So let's see what happens next. So, number of phases equal to 4. Phase components two plus 3 5 plus 2 7 plus 1 8 phase components at the moment. And then you have system components. Is equal to 5. Add to it, not 5, 7. 7 phase components according to you. According to, has been suggested, NCF mesh. So system components is 7. So if I look at the degree of variable, F is equal to C minus P plus 2, then C minus P plus 2. Then you have system components is 7, phases is 4 plus 2, and that is 7 plus 2, 9, and this is 5 degree of freedom. This is 5 degree of freedom. Now when I write 8, now you see here there is a problem. None of my compositions take structural water. None of the minerals take structural water. So I don't know where does this come from. I can't describe it because there is nothing here, but I take it. If you want, I take it. I wouldn't have taken it, but this can happen because of a different reason, but that is very much more difficult for you to understand. So here we have 7 system components. So degree of freedom now is 5. Be careful, 5. Okay, what are the number of independent reactions? Is number of phase components minus number of system components. So number of phase components, here you can see 8 phase components, and system components 7. Independent reaction 1. So So total 5 plus 1 is equal to 6. This should be the number of variables. This should be the number of variables. Now, what are my variables? Here, independent variables, right? So, number of variables is pressure and temperature, that's it. And here, either X dioxide or X Heidelbergite. X dioxide or X Heidelbergite, and or here. Then you have garnet, for which you can write X grossular, X almandine, or X pyro. Or you could reverse it, it doesn't matter. So, and for plagioclase, independent variable is XCA plage or XNA plage. This is what I see from the mineral assemblage. This is what I see from the mineral assemblage. So how many variables? 1, 2, 3, 4, 5, 6. Therefore, there are 6 variables. 1, 2, 3, either 4, 5, 6. XSiO2, SiO2 being pure, it is not a variable. XSiO2 is equal to 1, it's not a variable. XSiO2 is 1, it is quantified, so it's not a variable. So, here we have 6 metamorphic variables. Now, have you understood? Gibbs phase rule, at the moment F is equal to C minus P plus 2. Once again, let's recollect. As I see, there is no water here, but we have taken H. We have taken H. For reasons, I don't know. But there could be a reason, but that's more difficult, so we don't discuss this. We are already having a lot of problems. So number of phases for me is equal to 4. No doubt about it. Number of phase components, oh, here is a mistake. 3 plus 2, 5 plus 2, 7. This is a phase component which is 8. Right? Phase component is 8. So, system component, as you have given with H, 1, 2, 3, 4, 5, 6, 7. 7 system components. Degree of freedom, 7 minus 4 plus 2. So 7 plus 2, 9 minus 4, degree of freedom 5. Independent reaction, number of phase components, 8, minus system components, 6, 7 is equal to 6. Total is equal to 6. Right? What can you determine? What can you determine? What can you determine? Now you see. You can determine using an equipment the compositions of the phases. Right? Compositions of the phases. So I can determine X dioxide. I can determine X grossular, X almandine out of the independent variable. This also I can determine. I can also determine this. So I can determine all of these components. In fact, all of this. How many variables will I live with? 2. How many equations do I have? 1. You can't find it. You can't find it. You have 1 independent reaction. You have left with 2 variables. Somewhere you're wrong. Somewhere you're wrong. Somewhere you're wrong. I can find out X dioxide from a mineral analysis. I can find compositional, I can find out. Right? No problem. All the compositional phases can be found out. No problem here. So, I will be left with these 2 variables. I will be left with. But I have one equation left. So I have given the Gibbs phase rule says you give me 5 inputs. Where are my 5 inputs? There are no 5 inputs. There's 1, 2, 3, 4. 4 inputs. Where is 5? There's no 5. 4 inputs. I can only give you 4 inputs. Pressure, temperature, I want to find from the system. How do you want me to give a temperature? From where do I give it? This is my assemblage. From where will I give you temperature? I can't give you temperature. I can give you pressure. I can give you the compositions of the phases. I can't give you temperature and pressure. Temperature for you to find out the pressure. I don't have any more equations. I don't know. So there is something wrong with this system. But how can you, why, I don't know who suggested this. Either it could have been a printing mistake. If this is the assemblage and this is the system is wrong. Or else there are some riders which you may have missed. There are some riders which you may have missed. Even if I add fluid, I will not be able to solve it. You can try it. If I add a fluid means what? Fluid means, let's say a fluid is a phase. So if the fluid is a phase, if it's a phase, it can be H2O, it can be H2O, CO2, it can be anything, H2O, CO2, CH4, it can be even more complex. You can go on making it more complex, as complex as you want. But I will not be able to find out anything like this. Because from this, if I have to put H2O in a reaction, say for example, I write H2O. So if I have to write a reaction involving H2O, H2O should be balanced between left and right. If it is not there, then the reaction cannot be written and the quantification cannot be done. Do you see? So here is the problem. Here is the problem. This has come up because of NCF MASH. Now let's say what we do is, let's cross H. Let's cross H. The number of phases 4 remains the same. Number of phase components remains 8. Number of system component draws down to 6. Now you see here, this goes down. System components is now 6. So 6 plus 2, 8 minus 4, and this becomes 4 now. And now, so instead of 5, you have 4. Yes, you have 4. You can find out 4. Yes, right. An independent reaction, number of phases, 8 minus 6. This takes it to 2. Now you can find out pressure temperature conditions. You cannot deal with this H. Either it's a printing mistake where you have written it, or there is a complexity which you did not read, or there could be another thing. This garnet could be a hydrogrossular garnet which contains OH radical. Hydrogrossular garnets. So if that is the garnet, then OH radical gets into orthopyroxene. Or for example, very high pressure, very high pressure in the mantle, H2O occurs as a structural water within pyroxenes, garnets, etc. Within pyroxene and garnet, structural water is introduced due to substitution. If that is that, then your components has to change. Because these components don't take water. So there has to be a water-bearing component for pyroxene, and not only pyroxene, there has to be a water-bearing component for garnet as well. Because if you have OH in the phase component here, if you want to write a reaction, it has to be balanced somewhere else. So I don't know where you got this from. If you can get me the reference, I can go through it and see. But I guess what happened was, wherever you have read or whoever has told you, he was not being clear and conceptually clear. Either his pyroxenes contain OH structural level water and his garnet contains structural level water. It is possible. Hydroxylase is possible. High pressure garnets and high pressure pyroxene contain structural water. But then if you have structural water, these two are not the only components because they don't contain OH. These components are not enough because they don't contain OH. So if you have to constrain H2O, you have to write a reaction involving H2O. Otherwise, you can't take NCF MASH as you have written. No. Thermodynamically wrong. It is thermodynamically right if your pyroxene and garnet contain OH radical. But then your components have to change. High pressure mantle rocks containing clinopyroxene, garnet and plagioclase, they are considered within NCF MASH system. But in that NCF MASH system, the components of clinopyroxene and garnet are completely different. You either, when you have read it, you send me the article, or I can't do anything about it. But H2O, unless you have structural water somewhere, you cannot constrain H2O. And in the mantle, do you think it's right to take XH2 equal to 1? Not at all. As absolute garbage. H2O is not equal to 1, it's close to 0. Close to 0. It's fluid absent conditions. So even that fluid absent condition, your phases would still be 4. Phases would still be 4. But you have to find out a way to take in OH within the reactions. If you can't take it, you can't constrain it. That is the important thing. So, I don't know, you have to go back and read the paper or send me a PDF of the paper. I will go through it and tell you what is the problem. But as such, without an OH radical somewhere, any of the phases do not contain H2O, and you bring up an NCF MASH system, it has to be either a hydroxyl structurally held pyroxene and garnet. Otherwise, this is completely thermodynamically wrong. Right? Okay, I think I have been able to explain you all the 3 answers. You see, I will tell you, while I understand that this is a good forum to discuss things among the classmates, but sometimes, some of you ask me questions and I put it up in the forum, and the answers in the forum are not correct sometimes, which is expected. Your inexperience has to deal with it. But sometimes what happens, then I have to interject. I have to intervene in such cases, because I can't allow a wrong to be said and people without thinking accept it. But you see, the problem is I don't have my whole day sitting for metamorphic phase equilibria. I have other work to do. So sometimes I feel that, okay, where am I going to do my work? And sometimes I feel that I'm doing injustice to you. So I thought of today using 2 lectures to clarify whatever you have thought. But at the same time, you must realize that I got delayed in what I was supposed to teach. Yeah? So what I will do is at least this, because I want you to, the examination is on 9th February, so I wanted to complete a part so that I can leave it to you for studying and then appear for the exam. So what I will do instead here is I will take an extra lecture and upload it for you, so that at least I will be happy in my mind that, okay, I could do something for this, right? Thank you very much. I hope there is all clarification. And those where you said that it should be discussed in NCF MASH system, you please send me the paper, I will go through it, or you can get it clarified. I think it was because of a high pressure assemblage, but I don't know if it's a very high pressure, how does plagioclase come in? Because it's a very high pressure mantle assemblage. I don't know how plagioclase comes in. Or it might be a skarn rock with hydrogrossular, possible. If it's hydrogrossular, it's possible. Then you will require NCF mesh system. You will have OH structural water in that. You will have it. Of course you will have it. And then it would be right to treat it in NCF mesh system if you have hydrogrossular. Or if your clinopyroxene has structural water, then it should be in the mantle rocks, very high pressure. But then I don't know why plagioclase comes in, because plagioclase is a low pressure mantle rock. I don't know how plagioclase comes in. As you go down, your plagioclase reacts to produce olivine clinopyroxene garnet. So your clinopyroxene becomes more sodium rich. So I don't know how these are compatible, I can't tell you. Right? Thank you.